Alright, welcome to this video on roots of equations. That's going to be our topic today. So let's go ahead and dive right in. So up to this point in the series of videos that I've been making for this class, we've talked about why we want to use numerical methods, and we've also introduced you to some MATLAB programming. And so now we're actually going to dive in and start talking about the actual numerical methods and techniques that we use to solve different types of problems. And roots of equations is one type of problem that we can solve numerically. So kind of the motivation for finding roots, is we wish to solve some equation for an unknown. It's just the simplest way to put it. Okay? Now this can be very easy for simple equations, so this can be easy for simple equations. Such as linear equations, something that looks like 5x plus 3 is equal to 9, right? We can manipulate this algebraically and get x is equal to 6 over 5. So another way that we could have written that problem is as a root problem. We could have said, if I have the equation 5x plus 3 minus 9 equal to 0, what value of x right here makes this side 0? Or if this is the equation for a line, right here. So if I write this down as an equation for a line, y sub x equals 5x plus 3 minus 9, that's actually 5x minus 6, right? What we're finding is where y sub x intersects the x-axis. Where y sub x intersects the x-axis. So solving an equation for an unknown is the same thing as finding the roots of some equation. So the equation up here, we're solving this equation. It's an equation because we have an equality sign in here. Making it a root problem is we take everything and move it to one side of the equation so it's all set equal to 0. Then we take this, the non-zero side, write it down as a function and say find the roots of that function. The roots are where that equation, if you were to plot it, where it intersects the x-axis. So that's quite easy for linear equations. Also quadratic equations it's quite simple. So simple polynomials like quadratics, polynomials. So something like f of x equals ax squared plus bx plus c is equal to 0. This is just these are the coefficients to these terms, and we can solve it by factoring it, or we can use the quadratic equation, which just says the roots, so I'm going to call this xr, are equal to minus b plus or minus square root of b squared minus 4 times a times c all over 2a. So this is something that's taught in basic algebra. We use algebra to solve for roots of equations. Well, what happens if we get more difficult equations that we want to solve? So we run into problems. So, however, for more complex functions, complex equations, more complex equations, it can be difficult, very difficult, it can be difficult, or even impossible. To solve exactly. So let me give you some examples. One good example would be this equation. We have e to the minus x equal to x. There is no way that you can manipulate this equation algebraically to isolate x on one side of the equation. So you can't get it in the form of x equals something over here that's going to result in a number, some number, just using algebra. Can't do it. We can move everything over to one side like this, e to the minus x equals 0, but then we don't have some rule like the quadratic formula that tells us how to find the roots of this equation. There isn't one that exists, but there's clearly a root. So actually this function, one way you can figure out where the roots are is you could plot this function and see where it crosses the x-axis. Another way is you could plot this function right here, plot this function and this function and see where they intersect. That would be where the roots of this equation right here are. So we know that there is a root, there is a solution if we plot this function. This is x, this is our functions. So e to the minus x looks something like this. Comes down and it passes through 1 and asymptotically approaches 0 here. So this is 1. And then we know that x just looks like this. Oh, no, that's x plus 1. Hold on. X looks like this. Sorry. It's just a line, right? So this is f of x equals x, and this is f of x equals e to the minus x. And so right here, this is where they intersect. That is the root to this equation, e to the minus x equals 0. So we know there's a solution, we just don't know how to get it using algebra or any of the traditional techniques. And there's lots of equations that show up in science and engineering that are like this. Let me just give you a couple examples. So we talked about this falling parachutist example where we came up with an equation for the parachute's velocity as a function of the gravitational acceleration, its mass, its drag coefficient, and time. So here the question is, okay, so how would you determine the drag coefficient c needed in order to have a velocity of v equals 40 meters per second after falling for a time of 10 seconds if the mass is 61.8 kilograms? So if we have a number for v, a number for g, m, and t, the only thing that's variable is c. So we could try and solve for c, but this, you can't isolate c on one side of the equation by itself, because 1c is trapped up here in this exponential function, and you also have it out here. So it's just impossible. You have to use a different technique than algebra to solve this equation. Here's just another fluid mechanics problem. So if you have a sphere floating in some water, so the density of this sphere is less than the density of the water, the water level here, the height of this solid right here above the water level is given by this equation. Looks kind of crazy, but if we know the density of the density of water, the density of the solid, and the radius of the solid, then the only thing that's variable is h, and we technically could try and solve for that, but because of its nonlinear nature, this becomes very, very difficult to solve. It's doable, but it's just easier to use a numerical method. So that's what we're going to be talking about, is numerical methods for finding roots of equations. Finding roots. We'll just say finding roots, because numerical methods can be employed for any equation, no matter its complexity. So that allows us to come up with very accurate approximations for roots of equations or solutions when we're solving for some unknown in an equation. So there's two kind of classes of numerical methods. Two classes of numerical methods for finding roots. The two classes are bracketing methods and open methods. Now, in our book, the Shapra and Kennelly Computational Methods for Engineers book that we're using for my course, this is talked about in Chapter 5, and this is talked about in Chapter 6 for my students. Alright, so we're going to cover both of these, bracketing methods and open methods. We're going to talk about their differences, their strengths and weaknesses, and when you would want to use one over the other. So that's going to be kind of it for my introduction to finding roots using numerical methods and motivation. And now we're going to jump in and talk about bracketing methods directly, and I'll do that in another video. So